I think you know what we are going to do in this video, don't you? Yeah, I know that you do. You know how I work already. And in this video, well, I kind of spilt the beans in the last one. We're going to do another example problem. And here it is. So this example says, name each of the following. And it gives me all these little squiggly lines that looks like it's probably from Egypt or somewhere. And I'm going to have to figure out what to call these structures. And it's just a series of lines. Yeah, that's what we do in organic. That's part of what we do in organic, at least. So we're going to tackle each one of these. We're going to work on them one by one, of course. And we're going to take our time with them. And we're going to explain how we get the name the way that we do. Now, notice that each one of these double bonds, they are drawing it in a way that I can tell you if it is E or Z or cis or trans. Believe it or not, it's there. And one of the ways that I know it is that I'm seeing them draw the double bond, especially in B and in C, straight across. And I see the legs, one pointed up, one pointed down, one pointed up and one pointed down on each end. All right. For A, though, they're doing it as well. They've just turned it onto the side. That's all that they've done. So this is where we're going to start. And what I need you to realize is that with this particular structure in your mind, I just need you to take this structure around this double bond right there and just turn it a little bit counterclockwise. All right. So this way we can position that particular organic molecule in the proper way. So I'm just going to turn it this way, just slightly kink it. And on the left-hand side carbon, which is here, I have something that points down. And what that something is, it leads to a carbon. So that's a CH3 group. Now, there's not a fourth bond on there, but it's understood to be there. So that means the fourth bond has to point up like this, and that goes to a hydrogen. It's understood. All right, on the right-hand side, I can do the same type of argument. I've got two prongs, one up on top, one on the bottom. And the one up on top that points upward, if I turn this slightly left-handed, right, and straighten it out a little bit, looks like it's a 1, 2, 3, 4 carbon chain. All right, so 1, 2, 3, and 4. And then the fourth bond to that carbon's not drawn, but I know it points down because this one pointed slightly up. And this goes to a hydrogen. So it says to name it. Okay, and this includes a complete formal name, by the way, not just EZ or cis and trans. However, we're going to start with EZ or cis or trans first. So if I look at the way that this molecule's ordered, I see a hydrogen to the left, and there's only one of them, and I see a hydrogen to the right, there's only one of those. So this would be proper to name as cis or trans, but it also would be proper to name as E or Z as well. I'll let you make that determination. We'll write down both, but you can pick out which one you want to use because both of them are correct. It doesn't say give me E or Z. It also doesn't say give me cis or trans. It just says name them. So you have an option here. So the hydrogens are on opposite sides. If they're on opposite sides, then this is a trans molecule. Okay, the longest carbon chain here, I've got 1, 2, 3, 4, 5, 6, and 7. So this is a heptene with the ENE ending. On carbon number 2, because that's closest to the end, I have the double bond. And that's really it. I have no other substituents. I have no other groups that I have to take into consideration. Nothing. So this could be called trans 2-heptene. Well, or what I could do is I could name this as E or Z as well. All right, well, how would I do that? Well, if I look at the high priority groups, carbon beats out hydrogen, doesn't it? We've seen that before. there's my high priority group. On the right-hand side, carbon beats out hydrogen. So this is my high priority group. So these two high priorities are on opposite sides of each other. So if they're on opposite sides, then that means this would be labeled as an E as well. And I could write E with parentheses, 2-heptene, or if I wanted, I could also do a 2E, 2-heptene. It's not necessary. There's just one double bond. That's it. And that E has to go to that double bond. That's why this is okay with leaving it off. But if there was more than one double bond, then I would for sure put the number in front. That way you would know which double bond has which orientation. So in this example, there it is. The name, the proper name, is trans 2-heptene or E2-heptene. And again, one double bond, don't need a number because of that. All right, so now let's take a look at the second example. So for part B, they do a pretty good job. For part B, they set it up for me, and I don't have to kind of take my time and go through and try to order it the proper way. So part B, it is ready to go. I've got this carbon here, and I've got that carbon there. All right, so on the left-hand side, this leads to a carbon, right? That's a methyl group. So there's a carbon. And down here toward the bottom, that also leads to another carbon. This is an isopropyl group. Okay, so carbon and carbon, it's a tie. All right, I go on to my next atom. Well, this runs out. Just hydrogen left. And in the long chain, I can move on to another carbon. That's fine. And if I do that, then this is the high priority group because that carbon beats out the hydrogens that are up above. On the right-hand side, same kind of deal. I've got a carbon that points down, and the fourth bond that's not drawn, it's understood to be a hydrogen. So this is going to be my high priority group. Carbon has a higher atomic number than the hydrogen does. They both are on the same side, so that means this is a Z molecule. So I need to incorporate that into the name. All right, now I need to name the thing. I've already determined the orientation of it. It's a Z molecule. So now I need to go find my longest carbon chain and blah, 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 blah. All right, so longest carbon chain that includes the double bond. Well, I've got one carbon here, 2 carbon, 3 carbon, and I could probably just keep going this way. I mean, that will give me a longest carbon chain. It's a tie, whether I go left-handed or down, it doesn't matter. So I'm just going to circle that, and there's my longest carbon chain. Well, how many carbons is it? 1, 2, 3, 4, and 5. So this is a pentene. And at carbon number 2, that is where I have the double bond. That's closest to the end, so I have to number closest to that end, which is on the right-hand side. All right, so this is carbon 3, this is carbon 4, and this is carbon 5. Now, I've got this group that I need to worry with, and I've got that group that I need to worry with. Both of those are methyl groups. They lead to one carbon. Well, wait a minute. I thought you said that this was an isopropyl group. I did if you looked at just this molecule piece only. That is the proper isopropyl group. But folks, we destroyed that. When we incorporated IUPAC nomenclature, not common nomenclature, when we did IUPAC, the IUPAC longest carbon chain went through that. So I'm not going to name it an isopropyl. That got included in the longest carbon chain. It took care of that. So on carbon number 3 and on carbon number 4, I have methyl groups on each one of them. So this is going to be classified as a 3,4 dimethyl. 2 pentene. And now in the front, I can simply put Z. We know that that Z only goes to double bonds, which is why we put it in the very, very front. We also know that there's only one double bond. Well, how do I know that from the name? This was ene, and it wasn't a diene or a triene and so forth. There was only one double bond, so I only have one orientation in the molecule, and that Z orientation goes to that only double bond that we have in that molecule. So Z, 3,4-dimethyl, 2-pentene. All right, so there's B. Now, let's do the last one. The last one, they are pretty good with it as well. Okay, they set it up in the proper orientation that I like to see. It makes their job a little bit easier when that happens. So I've got a carbon to the left and a carbon to the right. All right, so on the left-hand side, this leads to a carbon and a carbon. It's a tie. I move on to the next. I have a carbon, and then this runs out. It's just hydrogens that are there. Because of that, this is my high priority group. All right, on the right-hand side, I have a carbon and a carbon. It's a tie. I move to the next. I have a carbon and a carbon. It's a tie. I move on to the next. Well, this kinks down to be a chlorine, and this runs out, so I'm left with hydrogens. Chlorine has a greater atomic number than hydrogen does, and as you can imagine, this also has the highest priority. These two groups are on the same side, so this is a Z molecule. Now let's talk about the longest carbon chain, because we're going to have to name this thing, right? So the longest carbon chain that includes the double bond. So if I look at this, it has to go through those two carbons. On the left-hand side, if I go down, there's just one carbon there. But if I go up, I can get two more into the parent chain. All right, so there's going to be my beginning of the longest carbon chain right there. Now, the other option over here to the side is which way do I go? Do I go down and include those two, or do I go up and include those two? Well, there's still two carbons no matter which way I go. The problem here, though, is that the chlorine is attached to the top two. And that's going to make my job to name this a little bit easier. And that's going to be the preferred way for me to go. I'm going to go ahead and include these two carbons, because how am I going to name this entire thing on its own if I don't? All right, we know how to name a two-carbon chain. That's ethyl group. But how do you name a two-carbon chain with a chlorine on it as a substituent? We don't know how to do that yet. There's no easy way to do that. So by default, it's going to make me go down into the double bond and back up to where the chlorine is going to be. And this is going to be my longest carbon chain right there. And we need to name all of those other groups that are coming off of that longest carbon chain. All right, so let's take our time and do this step by step. 1, 2, 3, 4, 5, and 6. There's 6 carbons in there in total. So I know this is going to be a hexene. Now, which way do I number from? I focus on that double bond. I give it the lowest number possible. So 1, 2, 3 from the left, or 1, 2, 3 from the right. It doesn't matter. So it's going to get a 3 no matter which direction that I go in. So I'm going to look for the other parts of the molecule that will make that decision for me. I need overall to get the lowest number possible. If I look to the right-hand side, I see a chlorine on the very first carbon there on the right-hand side, and I see an ethyl group that's a little bit more inward. If I look on the left-hand side, really the only kind of groups that I have over here is that methyl group, and that happens at carbon number 3. So if our job is to give as many of the substituents the lowest number possible, then it's going to force me to start my numbering system over here on the right. So that is carbon 1, this is carbon 2, that is carbon 3, here is carbon 4, there is carbon 5, and there is carbon 6. So what this means, I need to do it in alphabetical order. Methyl, M, ethyl, E, and chloro, C. So I'm going to start off with chloro first. And on the first carbon, I have the chloro that's hanging off. All right, now my E or my M. E comes next. That's my ethyl group. This is an ethyl group because there's 2 carbons. That happens on spot number 3. So this is a 3-ethyl. And then on spot number 4, I have a 1-carbon piece that's called a methyl group. And then in the very front, I'll write a Z. Again, there's only 1 double bond. That 1 double bond, that's the only thing that applies to E and Z. So I don't need to put a number in front of the Z, but I could if I wanted to write a 3Z, that's here, because that is where my double bond is located. I could do that. No one's going to scream at me. I'm not going to get points taken off. So 3Z, or just Z, 1-chloro, 3-ethyl, 4-methyl, 3-hexene is going to be the name of that organic. All right, so I think that we are pretty much finished at this point with nomenclature. All right, it might come back a little bit later on, but what I want to focus on in some of the next videos, we need to take a break. We need to take a mental break. And what I want to focus on is the stability of alkenes at this point. We've talked now about how to name them. We've gotten more familiar with them. We've talked a little bit about the geometry of that double bond, and we've talked about that it's very rigid and it's not going to turn and rotate on us. So we need to talk about the stability at this point. What goes on with the double bond? Is it stable? Does it last for a very long amount of time? Is it good or is it bad if a molecule has a double bond? That is what we need to talk about. And then if it does have a double bond, are there certain predictions that we can make on how stable that particular version is going to be? So in the next video, we're going to kind of turn course. We're going to take a different route. We're going to go down a different road. And that road is all about the stability of the alkenes at this point. So that's what we'll talk about next. If you need to take a break, take a break. Right now is a good time to stop. And then you can come back and we'll start on kind of a brand new topic in a way.